Let's start. Uh, so we were talking about how to draw phase diagrams. So I can just give you example of. We always draw the phase diagram based on the like pxy diagram, pressure composition diagram. So we always draw the diagram based on the more volatile, like can be any shape. You will see in my slide there will be different kinds of shapes, and this is called px1, this is py1, this is also called saturated liquid line, this is called also called bubble line, I told you how, and this one is saturated vapor line or dew line. So here we have subcooled liquid. In between we have VLE, two-phase system, vapor liquid equilibrium, and here we have maximum liquid, here we have maximum vapor, because these are saturated liquid line, saturated vapor line, and this is the superheated region. So let's see how we can draw these diagrams. This is your goal in exam. So we have very famous law for two-phase system, and that one is called Raoult's law. So Raoult's law states that partial pressure, this is partial pressure, equal to xi pi sat. Okay, so what is Dalton law? Dalton law is pi is equal to yi total pressure P. So this is the partial pressure, this is the total pressure, this is the vapor pressure. So if we equate both, we can come up with the equation yip equal to xi pi sat. So this is called Raoult's law, the main question of Raoult's law. In this question there are two terms. This term is for liquid phase and this term is for vapor phase. That's why this law applies to the VLE system. If you see here, we assume in this law, we assume the liquid vapor phase is the ideal gas vapor and the liquid phase is ideal solution. So there is one thing, the vapor behave as ideal gas. Second, the solution behave as ideal solution. So you are mixing two components, ethanol and water. So both are, if they are ideal solution, so we will discuss how they are ideal, what is ideal solution in next slide. But so the solution will behave as ideal solution and the vapor produced from that solution is behaving as ideal gas. And the third condition is this law is good for when x1 approaches to 1. It means this law is good for concentrated solution when your concentration of x1 is very high. Maybe you are familiar already in high school. You have already studied in high school that if the concentration is low, dilute solution, we have another law that is called Henry's law. So let's talk about what is ideal solution. So based on this question, we will solve the problem. So before that, we can talk about ideal solution. So the ideal solution is a solution that you can compare with the other solutions. Like, of course, no solution is ideal, but of course, if you mix two components like methanol, ethanol, so they belong to same family. So their molecular size, their molecular shape, their molecular properties, dimension, all are exactly same. Then they will behave like a pure component. They are two components, but when if their properties are same, their force of attraction is same, their force of repulsion is same, then this shows that the solution the solution of these two components behave ideal solution. So so their so like we have example of there is no ideal solution exists, but we can say hexane and heptane. They belong to same family hydrocarbons, and their molecular size, their molecular shape are close. Of course, this is big one, but they almost they have same, and their because they belong to same family hydrocarbon, so it means their properties will be same, their dimension, their force of attraction will be close to. I am not talking about methane and hexane. You see very close, C6, C7, almost close. Another example of ideal solution. Another one is benzene and methyl benzene. So there is another example. So propanol, one propanol, two propanol. So these are all examples of a close solution that behaving ideally. They are close to ideal. Like they have same nature, same properties, force of attraction. So once they mix, their heat of solution is zero. They don't release any heat, they don't absorb any heat. So I told you last time, if the solution is ideal, so it means they will give almost straight line. If you increase the composition, the pressure will increase at constant T. So, but we are getting curve. So there are two phenomena happen. One is ideal. So we will see there are two deviations. One is positive deviation and one is negative deviation. Okay, so we can draw the same curve, same diagram, x1, y1. So this is the ideal line. In negative deviation, you will get, this is your px1 line. Your px1 line is below the ideal line, and this is your py1 line. So this shows, the negative deviation shows your attractive forces are dominant. When your attractive forces are dominant, your P sat will decrease. Because the molecule attract each other, so your vapor pressure will go, less vapor will go up. So similarly, if you talk about the positive deviation, so this is the ideal line. Here we have P, x1, y1. Then your px1 will be up, py1 will be down. So in that case, this is the ideal line. Your x1 line, the px1 line is the bubble line or saturated liquid line, is above the ideal line. So in that case, your P sat will increase because repulsive forces are dominant. So attractive forces are dominant, repulsive forces are dominant. So we have deviation, negative deviation and positive deviation. So we also have one more, you can say the example. another side of diagram that you will see in my slide also. So in case of negative deviation, it may come like this shape. So this is called, this one is px1 and this one is py1. So again, the x1 line is below the ideal line, so it shows this is negative deviation, attractive forces are dominant. But these two curves join some point. You see, they bisect each other at one point. We don't know. So in next, maybe after 2 lectures, we will talk about in detail. But the book has introduced this point over here, so we need to talk. And this point is called azotrope. So when your x line and y line bisect at one point, this is called azotrope. And if it is on the negative side, we will call it minimum azotrope. Okay. So when the point, the x1 and y1 line bisect each other, we don't want in industry, like in distillation industry or in distillation practice or any absorption or whatever, we don't want the component behaving as ideal solution, and they behaving as we need to check first they are making azotrope or not, because if there is azotrope, this shows they both the vapor pressure are same. It means x is equal to y. It means their both p's are same. P and P for bubble line and P for dew line both are same. So it means you cannot separate them. So similarly, we can go up for the, we can have like this shape. Sorry. So this is called px1 and this is py1, and we have this point. This point we call it azotrope, but because this is on the maximum, this is on the positive side, we call it maximum azotrope. So you also have to see whether you also have to see the deviation from the ideal line is small or big. If it is small, it's called small deviation. If it is big, small negative deviation. This looks small negative deviation. If you get a big difference, then you can say a large negative deviation, and so on. So like we can maybe, let me see if we have example of any negative, like negative deviation. The common example is chloroform. See here, chloroform and acetone. So this is the example. In positive deviation, we have benzene, and ethyl alcohol. Any other example, like carbon disulfide, CS2 and acetone, chloroform and ethanol. So you can like see another example is chloroform, CHLO, RO, FORM, and ethanol. So if we mix, instead of acetone, we mix ethanol with chloroform, we get positive deviation. If we replace ethanol by acetone, we get negative deviation. So this is how the system, we need to see how the system behaves inside the solution. So let's see if we can have one example how we can draw this diagram. So this is the problem. So we have a binary system, which means two components. I told you one, if given, it means acetonitrile, you don't know is it more volatile or less volatile. we have to look at 1 and 2 points. So 1 means it's more volatile. It means all calculation will be based on number 1 component. Nitromethan is 2. So closely confirm the Rhodes law given the following 10 questions. So 10 questions are given. So let's say part A, very easy. What you need to do is, so we have two components, 1 and 2. So first part is we need to plot Px1 y1 at 75 Celsius. Okay, so first step is you need to find P1 set. So but before than that, or I can explain over here, it's not a big deal. So before that, so P1 set, so if you substitute this by using time question, we already discussed in chapter 6, just plug in this value over here and take the anti-log, it will give you answer. Let's say it comes out to be 83.21 kilopascal. Second step, you need to plug in this temperature over here. This will give you P2 set. It comes out to be 41.98 kilopascal. So we have two pressures. Then we need to find, so here what, we don't have any information given. We need to plot. If we need to plot, it means we need either x value or y value. So what we need to do is, we will write on x1 over here. We start the values from 0 to 1. We know the mole fraction cannot be more than 1 and the minimum is 0 value. So 0, 0.2, 0.4, 0.6, 0.8 and 1. If you like, you can take more values, 0.0, 0.1, 0.2, 0.3, 0.4, but you can save time. At least minimum you have to give me the solution in exam the 4 intervals like 0.2, 0.4, 0.6, 0.8. So then we need to apply Rhodes law. So if you see here, we know the Rhodes law definition. Y1 is equal to Y1P equal to X1 P1 set. Okay. Yi equal P equal to. So we can write down for one component Y1P equal to X1 P1 set. Y2 is equal, Y2P is equal to X2 P2 set. So if you sum up Y1 plus Y2 P common, it will be X1 P1 set, X2 P2 set. You can see. So the sum of mole fraction will be equal to 1. So question comes out to be X1 P1 set, X2 P2 set. So you can generalize P is equal to Xi Pi set. Similarly, so this is the equation for bubble line. So similarly, I can just write down the final version. Similarly, you can do for the dew line. So the dew line, so P is equal to, I can write down P bubble, PB and P dew. So this will be 1 over Yi over Pi set. So this is how we can write down, or you can, if you want to write, I don't have enough space, but 1 over Y1 over P1 set plus Y2 over P2 set. So this is for the dew line and this is for the bubble line. Let's see. So how we can solve the problem? You know x value. If you know the x value, you can calculate using this question, bubble line. If you know the y value, you can use this line, this question, and solve. So we know the x. What we need to do is we can plug in the value over here. P is equal to x1 p1 set, x2 p2 set. Then we can say p bubble if you like. So we need to plot, see, x, p, and y. No, y. So let's see, if x1 is 0, it means your p, x1 is 0, it means x2 is 1. So p will be p2 set. When x1 is 1, x2 will be 0, it means your p will be equal to p1 set. So we know already p2 set is 41.98 and p1 set is 83.21. So in between we can just plug in the values. We got here 50.23. So x2 means 1 minus x1. So you know x1 50.23. If you calculate, this will be 58.47. Then we have 66.72. And then we have 74.96. Then y1. So you know already the basic relation y1 is equal y1 p equal to x1 p1 set. So you can easily calculate x1 p1 set over p. So if x is 0, y will be 0. As x1 is 0. If x is 1, y will be 1. Only, so no need to calculate again. Only just calculate in between 4 values. So it comes out to 0.33, 13, 0.56, 92, 0.7483, 0.888. This is how we solve the problem. So if you plot x1 versus p, this will give you bubble line. And if you plot this p versus y1, this will give you dew line. No need to calculate by using this question. So even with one question, you can plot both. So if you plot x1 versus p, you can get bubble line. If you plot y1 versus p, you can get the dew line. So let's see how we can plot. So you are familiar how we can plot, but quickly we can go through. You see, all calculation I did based on x1 and y1. I didn't calculate anything except only p2 set is there. The remaining all values are based on x1 and y1. So we have x1, y1. So this is, let's say, 0.5, 0.6, 0.7, 0.8, 0.9, 0.4, 0.3, 0.2, 0.1. So similarly on the y-axis we have so we can say 10, 20, 30, 40, 50, 60, 70, 80, 90. So we have 10, here we have pressure, 30, 40, 50, 70, 80, 90. 0 to 1, 0.5. So let's see. So we have, so here will be P, x1 is 0 and x2 is pure. Here x1 is 1, x2 is 0. The first value at x1 0, first we plot bubble line. x1 0, p2 42. x1 0, p2 42. x1 0.2 and that one is 50. So 0.2 and 50. 0.4, 58. So 60. Then we have 0.6, 66.6. We go up somehow here. And 0.8, we have 75. 74.96, so it means 75. So 75 somehow here. And 1, 83. So 1, we have 80. So this is your bubble line. It's almost straight. It shows your liquid solution is behaving ideally for this one, acetonitrile and nitromethane. So this is your P2 set and this is your P1 set. Now let's see. Now we need to plot dew line. Y1 versus P. Y1 versus P. So 0, 0. So we have 50.33. So 0.2, 0.1, 0.2, 0.3, 0.33. Go up. And we have 50, 50. So go up. We got here point. Then we have 0.56, 58. So 0.5, 0.56. We have 58. Point 6, 67. So sorry, 0.74 or 0.75 you can say, 66. 0.7, 0.75. 66. Then we have 0.89 or 0.88, 75. 0.9, 0.88, 75, and this is the end. So you can see we are getting curve like that. So this is how we can plot. So this, then you have label. This is px1, this is py1, and this is the subcooled liquid. This is bubble line. This is dew line. A saturated liquid, saturated vapor, saturated liquid, and this is VLE. So you can see here the line state means shows that the solution is behaving ideally, but the vapors are not behaving ideal. So vapors are deviating. So but anyway, we will just we will not go in detail. So then we have superheated. So in exam you have to label like that, in quizzes, assignment, whatever. Superheated vapor. So this is how we can solve the problem in exam. So let's see part B. So let's see part B. So part B is plot Tx1 y1 diagram. Plot part B, plot Tx1 y1 diagram. So for that case, if you see, we can have temperature is given. So the temperature is given, so we need plots. So pressure is given. So pressure is given 70 kilopascal. Only one piece of information is given. So what we need to do is, so we can say plot at pressure this one. Now what we need to do is, again we have to do the same steps. Most of the steps are same. So you know already these two questions. So what we need to do is, this pressure we have to substitute here, 70 for part B, 70. Plug in here, you will get T1 set and T2 set. So at this pressure, you have 2 in 10 questions. You will get T1 set, that one is 69.84, and T2 set, and this is step 1. That one is 89.58 Celsius. Okay. Now what we need is, now we got 2 extreme values. Both are temperatures are saturated temperatures. So what we need is, we can just see the difference between them. So the difference seems to be 20. So what we can do, you can select any temperature in between these two values and solve the problem. But better way is, you can see the difference between them. This is 20. So what we do, we divide by, so let's say we have 69 and 89. So what I will do, I will write down again, make a table. You can see the full solution in my slide. So what I will do, I will just the third step, this one. So I will write temperature over here. Okay. So T1 set, and here T2 set. Okay. Here we have x1, and here we will have x2, or y1, sorry. What we need to do is, we can just 69 and 89. So this is 69, this is 89. So you can, because if we can take 70, we can do that, 70, then you have a lot of points to do. So better way is, like we did only 4 calculations in between, from 0 to 1 we did only 4 calculations, 1, 2, 3, 4 in between. So similarly, this is for 0 and this is for 1. Again this is 0 and this is 1. In between you can take 4 values. So better if you divide this equally spaced, like 69, another point you can take, like I have taken 74. So our T1 set is x10 means T2 set, sorry, and this one is 89. So it will be 69, this will be 89. Because x1 is 0, it shows T2 set.